I'm going to break the gas laws that we're taking a look at into at least 4 parts. So you might need to be sure that you go through each part to have a complete understanding. But this first part has to do with a kind of a set of gas laws that have something in common. So all of these gas laws kind of work in a similar way. What happens is, for example, Boyle was investigating the relationship between pressure and volume at a constant temperature. And what he found out is when you multiply pressure and volume, you always got a constant. So the product of pressure and volume is a constant. Now this in and of itself wouldn't be very helpful for us. So another way to write this relationship is to say, okay, my first pressure and my first volume must equal my second pressure and my second volume, because the product of the two are always a constant. Now this is true under the conditions that the temperature and the amount are held constant in the process. Now at first this seems a little daunting, because you might think, well, how can I learn all these things? Well, the gas laws that I'm giving you, or that we're working on today, you'll be given on the exam. Now, I'm not going to tell you what's held constant, but if you remember, there's 4 properties that describe a gas: pressure, volume, temperature, and amount. And so what you can do is, when you look in the gas law, like Boyle's law uses pressure and volume, well, that means temperature and amount are left out. So the ones that aren't in the gas law have to be held constant. So in this case, temperature and the amount are held constant. Now, Charles' law involved a different relationship. It was between volume and temperature, and it found that the relationship between volume and temperature is what we call inversely proportional. And so these actually end up being like ratios or divided. And so if you take the volume and divide it by the temperature, you always get a constant. Now, Gay-Lussac's law, it has to do with the pressure and the temperature and their relationship. The combined gas law really does look like the combination of the first 3 laws. And then Avogadro's law has to do with volume and the amount and their relationship. Now, in all of these gas laws, we can go back and decide which properties were held constant. So Charles' law uses volume and temperature. That means pressure and the amount are held constant. Gay-Lussac's law uses pressure and temperature. That leaves volume and the amount. Remember, because you have to have all 4 variables. The combined gas law used pressure, volume, and temperature, so only the amount is held constant. And in Avogadro's law, the volume and the amount are present, which means that the pressure and the temperature must be held constant. So in each of these gas laws, we're going to use them when we have a change in conditions. Now, there's one other thing that I find interesting about these gas laws and what they can tell us, and it actually allows us to predict what we think would happen, whether the property we're looking at would increase or decrease. Now, when 2 properties, when they both increase, we call that directly proportional. And if one of them increases while the other one decreases, they do the opposite, we call that inversely proportional. Now, 3 of the gas laws are all directly proportional, these 3. So again, what directly proportional means is that these the properties in the gas law are going to, proportional. I'm talking and writing at the same time. it means the two properties are going to change in the same direction. For example, Gay-Lussac's law with pressure and temperature. I like to think of my car tires with this one. And as the temperature of your car, so as you drive your car on the road, the friction of the tire on the road increases the temperature. So as the temperature inside of your car tire increases, that then, as a consequence of that, pressure is directly proportional to that. So as temperature increases, pressure increases. Or if you live somewhere really cold, then on a really cold morning, as the temperature drops below freezing, you may find a little light in your car going on saying you have low pressure. That's because as temperature decreases, the pressure is also going to decrease because they're directly proportional. Now, for the Boyle's law, it is inversely proportional. So inversely means these two properties respond in the opposite way. And you might automatically notice the difference. Charles, Gay-Lussac's, and the combined gas law are all set up as dividing. And the Gay-Lussac's the Boyle's gas law is set up as multiplying. And the multiplication, mathematically, these two things are inversely proportional. So this means as one thing increases, the other one decreases. I love to think of respiration and the mechanics of how air would flow in and out. So if you think about it very simply, when you inhale, what happens is your lungs, between their diaphragm, the motion of your diaphragm and your rib cage, your lungs expand. Okay, that the larger volume, so the volume increases, and so the pressure inside your lung decreases because they do the opposite. That decrease in pressure allows the air to flow in, and it causes we have inhalation. When you exhale, then now the movement of your diaphragm and your rib cage cause your lungs, the volume to decrease. So as the volume inside your lungs decrease, the pressure does the opposite. It increases, and then that causes air to go out. So Boyle's law and the inverse relationship between pressure and volume helps us understand why air flows in and flows out as we breathe. So I kind of love that. The combined gas law, you can see it kind of has a mixture of Boyle's, Charles, and Gay-Lussac's law. So within the combined gas law, we have both components that are directly and inversely proportional. So let's take a look at a gas law, and we'll pick which gas law to use and kind of see how these gas laws work. What I want you to know is I'm only going to do one problem in this particular video. However, if you look under class lessons, you can find a couple more examples for some of the gas laws. So looking at this problem, it says a sample of methane gas occupies a volume of 575. So I have a volume of 575 milliliters, and it's at negative 25 degrees Celsius. Now my personal preference is, I know I cannot use Celsius, so before I even go any further, I take and I add 273 to my negative. This is a negative 25, so negative 25 plus 273, and I get 248 Kelvin. So go right to Kelvin. And then I keep reading. It says, if the pressure remains constant, what will the new volume be? So it tells me I'm looking for a new volume if I change the temperature. So here I've set up a problem where I have an original temperature and an original volume, and they're asking me to change the temperature. In fact, I'm heating that temperature up to 37, so 37 plus 273, that's 310 Kelvin. Now before we go on, let's just see what we think will happen. So if I notice here, if I go from here to here, my temperature is increasing. And so which gas law am I going to want to use? I have volume and temperature. So looking back, I think I'm going to go ahead and use Charles' law, right? Because I have volume and temperature. Like I can't use Boyle's law, I don't know pressure. I can't use Gay-Lussac's law, I don't have pressure. So Charles' law fits the information I'm given. So I'm going to use Charles' law, which is V1 over T1 equals V2 over T2. Now this gas law is directly proportional, when it's one on top of the other. So if temperature increases, I'm going to say my volume increases. So we should have a volume that's larger than 575. So let's go ahead and plug it into our problem. So I have 575. I like to keep the units. You do not have to, if that's confusing to you. I don't know my volume. That's my question mark. And my new temperature is 310 Kelvin. Now you might want to pause it here and you just do the math yourself, because you don't have to follow how I do my math. I know, so you could pause it now and then turn it back on. I want to move the 310 to the other side, so I'm going to multiply by it. So I'll have 310 Kelvin, and then I have the 575 milliliters and the 248 Kelvin, which I already had there. And that will cancel out my Kelvin. So my units are milliliters, and to get the answer, I will take 310 times 575 and divide it by 248. And to three significant figures, my new volume would be, I have 718.75, so it's going to be 719 milliliters, which is does increase. Remember, I predicted the volume would increase, and it does increase. Now, kind of a fun thing or cool thing, I don't know how you want to put it, about this is, notice they told me it was CH4 or methane, and that's not really relevant to this problem, because these gas laws are good for any gas and any mixture of gases. So to solve this problem, I don't need methane. I don't need to know it's methane. And in the bigger picture, it doesn't matter that it's methane. Any gases under this condition and under this change of conditions would have this new volume. So I'm going to stop this video now. There's other parts that are going to talk about more of the gas laws. And again, in the under class lessons, there are some other problems that use Boyle's law and Charles' law as well.